Hello, we are on page 82 of your science book, Floating and Sinking. Okay, here we go. All right, here we go. Brady and Leo, be quiet and pay attention. 1912, the Titanic departs from England on its first and only voyage. At that time, it was the largest ship afloat, nearly 3 football fields long. You got to think about it, 1912, that's a big, big boat. The Titanic was also the most technologically advanced ship in existence. Its hull was actually designed with different compartments in it, where if one of them sprung a leak, that compartment would fill up with water, but the other compartments would not. And that would keep it from sinking. What they were not counting on was the fact that it was going to rip the entire side off the boat when it hits the iceberg. Okay? So that didn't work out too well. We're not talking about the Titanic. This is not history. Okay? We will study the Titanic shortly, and you can share your knowledge at that point in time. I would love to hear it. Okay? But they thought it was unsinkable because of that. Okay? Yet, a few days into the voyage, the Titanic struck an iceberg, one compartment after another filled up with water. In less than 3 hours, the bow of the great ship slipped under the waves, and as the stern rose into the air, the ship broke in two, and both pieces sank to the bottom of the Atlantic Ocean. More than 1,000 people passed away, and 2 dogs. Oh, now, so why is this thing called buoyancy? We're not talking about the Titanic necessarily. It was an example, folks. Yes, Peter.
Wasn't it because there was like the dog kennels on the thing and they couldn't
I
get out?
don't know. I don't even care right now about the doggy. It was 1912. He's been in doggy heaven a long time. Okay. Ships are designed to have buoyancy, the ability to float. How is it possible that that huge ship can float easily on the surface of water under certain conditions and then a few hours becomes a sunken wreck? To answer the question, we need to understand the buoyancy force, okay? And that's what we're going to talk about here. And gravity and buoyancy, okay? Both of them are forces, but they work in opposite directions, okay? You have probably experienced the buoyancy force if you've ever picked anything up that was in water, like you try to grab your friend up in the water. It's easier to pick up, okay? Okay? Than he would be if you were on land, okay? Water and other fluid exerts an upward force, okay? And that is the buoyancy force, and that acts on submerged objects, okay? The buoyancy force acts in the direction opposite of the force of gravity. So gravity is pulling down on objects. A buoyancy force is pushing up on objects.
Wait, is buoyancy force only in the water?
Get it? That's a good question. That's a good question. Okay. So the buoyancy force acts in the opposite direction of the force of gravity, so it makes an object feel lighter.
That's why you float up when you're on the bottom.
Very good. That's why you go up. Yeah.
I was on that because I drowned in that.
Okay. As you can see over here in the picture, remember we talked about air, when we talk about air pressure, the pressure above your head weighs as much as one of our activity buses sitting up here. Okay? So, but the reason it doesn't crush you or put you on the ground and hold you to the point that you can't move is because that same amount of pressure is coming in from all directions, including upward. So it equals out. Okay? And that's the same way the buoyancy force is. It's coming up from the different directions. And that's why some things will float. Okay? And we're going to talk about why in a second. Okay? A fluid exerts pressure on all surfaces of a submerged object. Since the pressure in the fluid increases with depth, the upward pressure on the bottom of the object is greater. Think about when you dive down to the bottom of a pool, even if it's only 10 foot deep. The pressure is more down at 10 feet, right? Yeah, because your ears will start popping and all the whole bit. Yeah.
When you do it this
All right.
it hurts.
Yes, Gail.
So like, if you ever think about going, like, you know, like submarines, they have to think about the pressure, because going too far down, the pressure is so much that it can crush it.
Yeah, it can. It can. Yes, sir.
I like going to the pool, like, every
jump down in 12 feet and go to the bottom?
We're talking about swimming in deep water, you know.
But my ears don't pop.
And now we're going to keep talking about it. Okay.
I have a swimming pool in my house. I go to it.
Yes, Catherine.
But if a person goes down to the abyss, then they'd be crushed.
Oh, yeah.
So
Easily.
why would it?
You can only get so deep.
Like,
As a person, you can only go so deep, and the pressure at that point in time gets so
I
great.
think
it
the
will actually
farthest
crush
I've
you.
ever gone underwater
Yeah.
is like 12 feet.
Yeah, me.
Okay. That's why scuba divers, when they come back up, they can't come back up faster than their air bubbles. If they do, the pressure actually messes with them, and they get what they call the bends, and it will start to tie their muscles in knots and everything, and they have to be decompressed in order to get over that. That's why you can't just go rent scuba gear and go scuba diving in the ocean. You've actually got to be trained so you know what the heck to do. Okay, that's why. Okay, all right. Remember that the weight of a submerged object is a downward force. If an object weight is greater than the buoyancy force, that net force acts upon the object. The object will sink, and the weight of an object is equal to the buoyancy force. No net force acts on that object. Now that's a rigmarole right there. We're going to do some experiments tomorrow that will help explain this a little bit better. Okay?
Yeah, I don't get this.
And you're not going to until we demonstrate it. It's going to be harder to understand. Okay? A submerged object whose weight is equal to the buoyancy force has no net force acting on it. Okay? So it shows you like a jellyfish and a turtle. Okay? They've got, the weight is pulling them down, but the buoyancy force is pushing up at the same. So they have no net, okay, no net force there. That is why sea creatures can get to be so big, because of the buoyancy force. Okay? They're not being, their weight does not crush their own skeleton system because of the buoyancy force.
yeah, because
Okay?
gravity's pushing down, and the buoyancy force, I think that's how you say it,
Yeah.
pushing up. So then it basically, it kind of evens everything out.
All right, now think about this. You go to a river somewhere and you take a log and get it rolling down the hill and get it in the water, and it will go floating down stream. Okay? But yet you can take that little bitty pebble and go toss it out and it sinks. Okay? Because of density and the buoyancy force, okay? That's what they're talking about. That tree is spread out more. That's why boats will float. They are spread out. Okay? If you take, and we're going to talk about that in a second, if you take that block of steel that a ship is made of and just throw it in the water, it's going to sink. Okay? If it's just a big block of steel, it's going to sink to the bottom. But if you take it and you roll that thing out, and you make it really big, it will float. Same weight, but it will float because it's displacing enough water now that the buoyancy force will hold it up.
Then
Okay?
you have to have all the people on
Okay.
it. It would be really stressful.
Yes.
So if you fall from like a really high height and hit water,
It's like hitting concrete.
yeah, but I'm like, I know that would kill you if not really hurt you. Can the boot? I know that.
Where are you going? What's that got to do with buoyancy? We're talking about you hitting the top of the water and it's like concrete. So floating is the least of your worries.
Well,
Mrs.
yeah.
Stassel,
Yes.
isn't the reason you hit it so fast, like when you hit it so fast, the molecules compress for a second, and that kills you, and then you see
No, you
that.
just
Well, yeah, it's not like you hit it and you just lay on top. I mean,
No, Leo.
okay, we're not talking about jumping off something and killing yourself, hitting water. Okay, that's not where we're headed here. Yes, Caleb. Yes, Caleb.
But then, aren't some people, aren't you able to jump off a high place if you're in the right position and they go like that?
If you time it correctly,
Yeah,
no one's ever come off the top of the Golden Gate Bridge and survived.
yeah. A lot of people jump off. But like some people, like some
That-
swimmers can jump off.
Yeah, but again, that's not
They go in
where
like
we're
that.
we're not.
and some
We're not talking about cliff divers. That's not where we're at. We're not talking about how you enter water. We're talking about what floats and what sinks. Y'all, why do y'all do this? You know I'm recording the class, and yet you will do things like this. Why? Why? Okay. once I turn this off, if you want to ask questions about, well, how about a cliff diver that, you know, we can explore that later, but it has nothing to do with what we're doing in class, okay? You can't tell me you missed it. Come on back. Be part of this. You won't learn anything, but gosh, it's so much fun. Okay.
Well, just let it do like this.
Archimedes principle. No, great questions, just off topic. Okay. All right. This is some of the experiments we're going to do tomorrow. Archimedes, everybody knows who he is, right? He was a guy that the king took some gold to this guy to make him a crown. And when he gets it back, he suspects that the guy maybe lifted some of the gold. So he challenges Archimedes to come up with a way to figure it out. So what Archimedes does, he takes the same amount of gold that the king had given the guy, and he puts it in water, a tub of water. And he marks how much the water rose up. Okay? Then he takes the crown, he puts it in the water, and he marks how much it raises up. And it doesn't raise up the same amount.
That's just smart.
It's supposed to weigh the same, but it doesn't. Okay? So the guy was indeed lifting some of the gold from the king. Okay?
Smart.
And then theory has it that once he figures this out, he runs down the street hollering, "Eureka, Eureka." Okay? So I don't know if any of that is true, but that's what they say.
What does that
He
mean?
sounds like a really psychic guy.
He was excited. Okay? So, you know that all objects take up space, and this is true. A submerged object displaces or takes that place of a volume of fluid equal to its own volume. If we had if you marked it, a swimming pool, okay, and you actually marked how high the water was before anyone got in it, and you threw a whole bunch of people in this pool now, and then went back, the water level is actually going to have gone up.
Because their mass will
Because
displace the
they're
water.
taking, the space they're taking up, the water has to go somewhere, and so the water goes up, okay? And it goes up based on the amount of weight that is, or the weight of the water being displaced. It's going to rise up that much. Tomorrow, I'm going to try to make a little thing tonight with a cup and a straw where we can test this theory, and when we put something in it, it will raise up, displace it, come out the straw. We can measure it and see if it works.
Oh,
Okay?
like the thing in the picture up here.
Well, they just kind of got it running over, but I'm going to actually try to catch it. If all else fails, we'll try this, yes. Okay? All right, now, Archimedes was a mathematician in ancient Greek, and he discovers a connection between the weight of a fluid displaced by an object and the buoyancy force acting on it. Okay? So this connection is known as the Archimedes principle. And it states that buoyancy force acting on a submerged object is equal to the weight of the fluid the object displaces. That's a rigmarole. Okay? Do you understand that, what this means? Think about a swimming pool again. Okay? If it displaces 50 liters of water, the buoyancy force exerted on you would be equal to the weight of 50 liters of water, or about 500 newtons. Okay? You can use the Archimedes principle to explain why a ship floats on the surface, since the buoyancy force equals the weight of a displaced fluid. The buoyancy force will increase if more fluid is displaced. A large object displaces more fluid than a small object, obviously. Okay, the heavier it is. If we had a tub of water and Morgan got in it, she's going to displace a certain amount of water. She gets out and goes on. I come, I get in. I'm going to displace more water.
Really?
Okay, because I weigh just a little bit more than Morgan. Okay, probably 20 pounds or so. Okay.
Really weighs 20 pounds.
All right. So since a ship displaces more water than a block of steel, a greater buoyancy force acts on the ship. Okay, that's what they're showing you up there. That if you just took a block of steel that they make that ship out of, but it's just a big block, and they throw it in the water, it's going to sink. Okay? But if they take it and they form it into a hull of a ship, it floats. Okay, because it is spread out, so it displaces. Water's density is like 1 gram slash, no, 1 gram slash centimeters cubed. Okay? You will. So anything that is more than 1 sinks. Anything less than 1 floats. Okay? That's simple. Okay? So density. What exactly why do some objects float and others sink? It's because of their density. Okay? The density of a substance is its mass per unit volume. So density equals mass over volume. For example, 1 cubic centimeter, and that's a cm3, of lead has a mass of 11.3 grams. So its density is 11.3 grams slash centimeters cubed. In contrast, 1 cubic centimeter of cork has a mass of only about 0.25 grams. So its density would be 0.25 grams slash centimeters cubed. So lead is more dense than cork. And the lead would definitely sink. Okay? Cork would float. Tomorrow we will do some experiments. We will do some different liquids, showing you how they will float on top of, some things will float on top of each other. If you ever notice, anytime there's an oil spill in the ocean, one of the reasons they can get it cleaned up is the fact that it floats on top of the water. The bad part is it's in the ocean, it spreads, but they can get it cleaned up. But it's because oil will actually float on top of water. You wouldn't think so, but it will.
So anything with a density over than 1 point or whatever,
Yep,
you know, is it gonna sink?
will sink. Unless it, again, and the reason a boat will float is because it's spread out so much that it is per centimeter, it is less than 1.
Yeah.
Okay?
But then, like the block of steel, it's so confined.
It's so confined that
that it's not much density.
it's not, yeah, that's it. Exactly. Exactly. Okay? And you can change density, and we're going to do an experiments tomorrow to prove that. We're going to change the density of water. Okay? Ice is one way that the density of water changes. Okay? Ice is one of the few things when it freezes, it actually gets larger. Okay? Most things when they freeze, they get smaller, right? They contract. Ice actually expands when it freezes because of the way the molecules are set up. It actually expands outward. If you ever filled an ice tray up and you filled it to the top, and then when it freezes, it's hard to break it because it's got that layer of water that has frozen along the top. That's because it expands upward. The water expands as it freezes, so it makes it harder. Okay? So next time you fill up the ice tray, you don't have to fill it all the way to the top. But it'll be full by the time when you get there. Okay? All right. You can make an object sink or float in a fluid by changing its density. To see how that happens, think about a submarine. Caleb was talking about submarines just a second ago. The overall mass of the submarine increases since its volume remains the same. Its density increases when mass increases. So the submarine will dive, and to make the submarine float to the surface, water is actually pumped out, decreasing its mass. Because they'll take water on in certain compartments to help them to go underwater. And then when they want to rise back up, they pump that water back out. And it'll come back up. Okay? If you fill a balloon with just air, okay, you blow it up, it doesn't float, right? It'll sink to the floor. Okay? Because that air is inside, is under pressure. Okay? But if you fill it with helium, what happens?
It floats.
It floats away because that's a gas and it is actually lighter than air. So you have changed the density there. Okay? Okay. Tomorrow, like I said, we'll do some experiments, and hopefully that will help explain this a little bit easier. And we'll see you tomorrow.